The last question that I will discuss today is question 8 from the May 2016 paper. It consists of 3 parts, 2 of which A and B you can see here, and part C is in a different page, and we'll get to that in a few minutes. So this is a question about conservation law. So luckily for us, part A essentially starts by reminding us of where conservation laws come from. So we have if we have 2 quantities rho and j defined in terms of a field U and its derivatives, which satisfy the continuity equation rho t plus jx equals 0, where subscripts denote partial derivative, what condition should we impose on the limits of j as x goes to plus and minus infinity to ensure that the integral of the charge density rho over space is a conserved charge? And then we need to justify our answer. So the condition is that j has the same limits at plus and minus infinity, that I will denote often like this, or equivalently by saying that the limit as x goes to minus infinity of j is the same as the limit as x goes to plus infinity of j, and we assume that the 2 limits are finite. And the justification is as follows. So let's compute the derivative with respect to time of this charge q integral of rho dx. So we can bring the time derivative inside the integral, and it will become a partial derivative with respect to t. Then we can use the continuity equation here. So partial derivative of rho with respect to t is equal to minus a partial derivative of j, the current with respect to x. And now this is an integral of a total derivative, so it's easily integrated to minus j, evaluated between minus infinity and plus infinity. And so this is 0, and the charge q is conserved, so does not depend on time, precisely if the condition that we wrote there above is satisfied. So part B applies these ideas to the mkdv equation, which is written over there, ut plus 6u squared ux plus uxxx equals 0. And we want to find 3 conserved quantities which involve u squared, and u to the 4th respectively. And we'll use boundary conditions that u and its first 3 special derivatives tend to 0 as x goes to minus infinity and plus infinity. So let's start with u. So let's try charge density rho equal to u. So then we compute its time derivative. So rho t is ut, and now we can use the mkdv equation to write this as minus 6u squared ux plus u xxx, and this is a total x derivative. It's the x derivative of 2u cubed plus uxx. So we identify this with minus jx. So we take rho equal u and j equal 2u cubed plus uxx. And now j tends to 0 as x goes to plus or minus infinity by the boundary conditions above. And so the integral with respect to x of rho, which is u, is conserved. Okay, so next we want to do the same exercise with u squared. So let's try rho equal to u squared. So then we compute its time derivative, so that's 2u ut. Then we use the MKdV equation to write this as minus 2u times 6u squared ux plus uxxx. Now we would like to express this as a total x derivatives if possible. So the first term is minus 12 u cubed ux, and the next term is minus 2u uxxx. So we can rewrite this as, so the first term is a total x derivative of 3u to the fourth. So for the second term, we can write this as a total derivative of 2u or minus 2u uxx. But then we need to add back the derivative of 2u times the second derivative of u, so ux. And finally, this last term is also a total x derivative. It's the x derivative of ux squared. So we can write this as minus 3u to the fourth plus 2u uxx plus, or rather minus ux squared, all differentiated with respect to x. So indeed, we can take the u squared to be our charge density, and then the current is the quantity in bracket, 3u to the fourth plus 2u uxx minus ux squared. And once again, by the boundary conditions, this goes to 0 at spatial infinity. And therefore, by what we've written in part A, the integral over x of the charge density u squared is conserved, meaning that it does not depend on time. Okay, so finally we need to find the conserved quantity, which involves u to the fourth. So let's now try rho equal to u to the fourth. So here it's going to be slightly more complicated. So we need to take the time derivative of u to the fourth. This is 4u cubed times ut. And then we use, once again, the MKdV equation. So that's minus 4u cubed times 6u squared ux plus uxxx, which we can also write as minus 24u to the 5ux minus 4u cubed uxxx. Okay, so the first term is a total derivative of 4u to the 6th. So for the second term, we can write it as a total derivative of 4u cubed uxx. But then again, we have to add back the derivative of 4u cubed times uxx. So that's plus 12 u squared ux uxx. Okay, so here it's not perhaps so obvious how to proceed, but we can note that, so we have a term, so in the last term we have a factor of u squared ux, which also appears in the MKdV equation here. So we're gonna rewrite this bit here using the MKdV equation. So let's do that. So the first term, I'll leave it as it is. And for the next term, I'm gonna write this at minus 2 ut plus uxxx times uxx using the MKdV equation above. Okay, so And I forgot, sorry, partial derivative with respect to x in the bracket above. So now we can use, we can massage a little bit more the last term again. So let me actually copy now the quantity in brackets. So next we have minus 2 ut uxx, and I can write that as the derivative of minus t ut ux with respect to x. But then we'll have to add back to utx ux. So these two terms here reproduce this times that. And finally, we had minus 2 uxxx uxx, and that's a total x derivative of plus uxx squared. Okay, so we're not quite done yet, but we can observe that the last term now, while it's not a total x derivative of something, is a total t derivative of something. So we can write this as minus 4 u to the 6 plus 4 u cubed uxx plus 2 ut ux plus uxx squared derivative with respect to x plus ux squared derivative with respect to t. And so if I bring this to the left-hand side, we can write that the time derivative of u to the 4th minus ux squared is equal to minus the x derivative of 4 u to the 6th plus 4 u cubed uxx plus 2 ut ux plus uxx squared. Okay, so this is where we are. So now we can interpret the brackets on the left-hand side as rho, which is u to the 4th minus ux squared, and the bracket on the right-hand side as j, that's 4u to the 6th plus 4u cubed uxx plus 2 ut ux plus uxx squared. And when x goes to plus or minus infinity, by the boundary conditions, j tends to 0. And therefore, what we reviewed in part A, the integral over x of rho, the charge density, which is u to the 4th minus ux squared, is a conserved charge, meaning that it does not depend on time. So this concludes the solution of part B. So part C applies some of the ideas of the previous part. So we have a field U which solves the rescaled Burger's equation given by the equation here, with the boundary conditions that ux goes to 0 at special infinity and u goes to u0 at minus infinity and to u1 at plus infinity, where we also take u0 to be greater than u1. There are three parts here. So in the first part, we take rho equal to u. And we want to show that if rho is equal to u, then there exists a j to be determined such that the continuity equation holds. But we need to explain why in this case it's not possible to define an associated conserved charge by the integral of the charge density. So the continuity equation holds, so it will have to be the case that the condition on the limits of j, the limits of j at plus and minus infinity do not agree. So let's see if that is the case. So we take rho equal to u and want to compute rho t, which is ut. Then we use Burger's equation to say that ut is equal to minus 2u ux minus uxx. And then this is indeed the total derivative with respect to x of u squared minus ux. So we identify the quantity on the right-hand side as minus jx. So j is equal to u squared minus ux. Now we look at the limits of j as x goes to minus infinity and plus infinity. So when x goes to plus or minus infinity, we are instructed that the time the x derivative of u goes to 0. So we just have to take the limit of u squared, and u goes to u0 at minus infinity, so the limit of j will become u0 squared. Whereas at plus infinity, u goes to u1, so the limit of j is u1 squared. And since u0 and u1 are different, then these two limits are different. So by what we deduced earlier, we know that q, which is the integral over x from minus infinity to plus infinity of the charge density u, is not conserved. So its time derivative will be related to the difference of these two limits of j as x goes to plus and minus infinity. Incidentally, let me also mention that in this case, actually this charge q given by the integral over x of u, not only it's not conserved, but it's also infinite, essentially, because u doesn't go to 0 at plus and minus infinity. Next, in part 2, we integrate the density u, not from minus to plus infinity, but between a and b, two real numbers. So we have qab is integral dx of u from a to b, where a is less than b. And we are asked to use the results from part A to find an expression for the time derivative of qab with respect to t in terms of the values taken by u and its derivative at x equal a and x equal b. So let's compute the time derivative of qab. We can take the derivative inside the integral, but now it becomes a partial derivative. And next we can use that this is equal to minus the x derivative of the current, because of the continuity equation where the current j is the one written above there. And so this is equal to minus j evaluated at b and evaluated at a. So this is equal to j of a minus j of b, which we can also rewrite using the expression above for the current as u of a squared minus u of b squared minus ux of a plus ux of b. So next, we're asked what is the limit of this time derivative of qab as a goes to minus infinity and b goes to plus infinity. So let's take that limit. So we'll have the limits of the expression that we obtained there. And the boundary conditions, I remind you, were that ux goes to 0 at plus or minus infinity, so the last two terms will not contribute, but u of a becomes u of minus infinity, which was u0, whereas u of b becomes u of plus infinity, which is u1. So this is nothing but u0 squared minus u1 squared. So let me call this equation star because I will use it shortly. So that concludes part 2. So finally, in part 3, we are told that u, which is a function of x and t, is now a traveling wave solution to Berger's equation, which satisfies the boundary conditions that we discussed earlier. And we want to find an alternative expression of the time derivative of QAB, which involves the velocity v. So let's first do that. So note that here we're told that u is a traveling wave solution, but we don't have to find this traveling wave solution. So I will not plug this expression for u into Berger's equation, but I will use it to study what happens to the time derivative of this charge QAB. So if u of x and t is equal to f function of x minus vt, then the time derivative of u, partial derivative of u with respect to time, is equal to minus v times the first derivative of f, but that's also equal to minus v times the partial derivative of u with respect to x. So I will just use the fact that ut is equal to minus v ux. So because now we can find indeed an alternative expression for d by dt of QAB, which involves v as follows. So QAB was integral dx from a to b of u, and we need to take the time derivative. So we have ut in the integrand. And next I use the previous expression that holds in the case of a traveling wave solution. So ut is equal to minus v, which is a constant, so I can take outside the integral. And then we have dx ux. And then we can easily integrate this. So that's minus v times u evaluated between a and b. So that's v times u of a minus u of b. Okay, so that's the alternative expression for d by dt of QAB, which involves v. Okay, so then we want to compute the limit of this expression as a goes to minus infinity and b goes to plus infinity. So let's do that. When a goes to minus infinity, we get the limit of u as a goes to minus infinity. That's what was called u0. And when b goes to plus infinity, the second term is minus the limit of u as x goes to plus infinity, which was called u1. So that's equation double star. And now we can compare the equation with 1 star and the equation with 2 stars. There are two alternative expressions for the same quantity, the limit of d by dt of QAB. So by comparing, so equation star is the same as equation double star. So we get that on the left-hand side, we have u0 squared minus u1 squared, which you can factorize into u0 minus u1 times u0 plus u1. And on the right-hand side, we have v times u0 minus u1. So after simplifying, we get that v is equal to u0 plus u1. And the question asks us to show that p is proportional to u0 plus u1. And we have to determine the constant k, the proportionality factor. And in the case, we see that k, or rather kappa, is equal to 1. So this concludes part 3 of part C.